let's start by talking about the homework from last time. We'll kind of go over this together. If you would, while we do this though, if you can take out your identity sheet while we do this, I think that'll be helpful to have out and looking at. So as we refer to using an identity here or there, you can check and see which identities it is that we're using and follow along and participate a little bit better, because again, I would like your guys's input on kind of like what you think we should do, and if there's a massively better way to do it. When we finish, I'll show you guys what I would have done in that case, like last time. So we'll just, I'll let you do whatever it is you want to do to illustrate the fact that as long as you're not breaking algebra rules, you'll eventually run into the correct answer. But I think, again, it's important that you kind of play out your line of thinking to kind of see what works or what doesn't work, or at least play it out long enough to be yeah, okay, so I think I've done too much. There must be a right answer closer than this one. Let me try something else and start over again, which is fine to do as well. But I think that this is an important part of you guys developing some intuition on how to deal with these sorts of problems. Okay? So let's take a look at number 11. And so you can either look for an algebra thing or an identity thing to do here. Do we see any obvious algebra thing to do with this? No, there's nothing really to do there, right? There's no terms to combine. It's already one fraction. There's no obvious factoring or FOILing or anything to do with that. So probably looking for an identity would be the first thing we'd want to do. I mean, there's lots of things you could do. I don't know why you would use one of the C's, considering there's no pi over 2's anywhere. So, again, it doesn't really matter. You can end up at the right answer kind of regardless of what you choose. So I've heard a couple of suggestions, people saying Q's and R's, and can we be a little bit more specific on what you want to do to what? There's 6 R's and there's 2 Q's, and there's 2 versions of each of those Q's, so. C2? Why would you want to introduce pi over 2 minus thetas in here when you already have everything as one variable? What? You want to use R2? That's so you can say using R2 we would say this, then, I guess, right? If you use R2, we're going to replace secant with 1 over cosine. Oops. Callie? So, Hallie, can you say that again so everybody can hear?
Sure. Okay. So if you use P1 and P3, could you change the sign into 1 minus cosine squared theta? But the 1 to 1.
How about an even better idea using P1? What if, I notice that I have a sine squared and a cosine squared here, right?
Oh, you just equal up to 1.
Yeah. Now, Hallie, we would have ended up at the same place doing what you had suggested. It just would have taken a couple of extra steps, but that's the right idea. So, okay. Now, Hallie, you had a bit more that you wanted to do here. What else did you want to do? Or take a look at P3 as it originally sits. Maybe that's the better route, right? Okay.
Okay, and that's just gonna equal secant. Oh, that's your answer. Secant, oh, yeah. Wherever that is.
Where we just reduced.
What is that thing?
What thing?
That little, is that a B?
That's the Greek letter beta.
Oh, okay.
It's like a B with a tail on it. Yep. Hey, ladies, can we put our cell phones away and stop talking, please? Thank you. That's as quick as you could have done that one. That would have been the best route through it.
Is that what you would have done?
Yep. So, again, doing what you had suggested in the beginning, turning that into cosine, was not wrong. You could have certainly, like, multiplied that cosine, like, multiplied by the reciprocal to get rid of the fraction, and you would have been left, moving some stuff around, but you could have ended up still at the same place. It would have taken quite a bit longer. In general, though, so we ended up starting with the Pythagoreans, right? Hallie, what did you see in this problem that made you think that the Pythagoreans would be a good place to look at?
I just kind of saw all the different ones,
Mm-hmm.
and then when they're telling me about the different ones.
Okay, specifically on the numerator, you saw the squareds. So when I see a squared, like something squared in my problem, I'm going to at least look at the Pythagoreans first. Oftentimes, those are going to be really useful when you have squared things in there, especially if things are being added together or subtracted, because the Pythagoreans all involve that addition and subtraction. So oftentimes that'll be helpful, as opposed to if I just have it like inside of a fraction, right? If it was the denominator of a fraction, maybe I'm less interested in using a Pythagorean there, because now you have a sum in the fraction. That's usually worse than having no addition in a fraction. So those two, kind of the addition and then the squareds in the numerator, should have been a good clue to look at the Pythagoreans first. Let's look at 12. Yeah. What did you see about this problem that made you look for the odd evens?
The secant of x is just secant, or secant of negative x is secant.
Okay, so Lexi's saying that what she noticed to make her want to use the odd-even identities here was that we had a negative sign on our x. So when we used the odd-even identity 5, that turned secant of negative x into just secant x. And when we did the odd-even identity 2, that turns cosine of negative x just into cosine of x. Those are what the odd-even identities 2 and 5 state specifically. So look at those at the very bottom there, Matt. Right? Okay?
And then can we change secant to 1 over cosine?
We can.
And all of that.
Yeah. So when we apply R5, secant becomes 1 over cosine.
And 1 over cosine times cosine is normal.
Yeah. And that's correct.
And that's the answer.
Mhm. Yep. That just says reduce. R-E-D. So if I look at R5, it says that secant is equal to 1 over cosine. So the highlighted yellow secant in the step before has turned into the 1 over cosine in the step after. Okay, and what's 1 over cosine times cosine?
Cosine.
1. That's why we did it. So that we could get rid of some trig functions. So that one was good. You guys did a good job there. Yeah. Okay. What do we see that we can do here?
I would say that. Is that multiply secant is that multiplying times cosine?
Uh-huh.
Okay.
Hallie, what were you going to say? Good. So Hallie says that this we can use C1 on to turn that into sine. And Hallie, what did you see in the starting problem that made you look at the C's to start with? The pi over 2. So that allowed us to turn cosine of pi over 2 into sine of pi over 2. Or so just sine. Sorry. Why is there a...
Oh, I see. Yeah.
Those are the alphas.
Yeah.
You're welcome. Okay. What should we do next?
Can we add the two sines together?
What do you guys think?
Maybe 2 sines.
Yeah. Yeah. So remember that when we add, the coefficient's going to change, not the exponent. So sine plus sine is 2 sine, not sine squared. So just make sure you're mindful of that. But yeah, so we just did some combining of like terms there. Matt? So we don't have anything squared though, right? So the Pythagorean is sine squared plus cosine squared is equal to 1. So we need to have something squared in order to use that, and we don't right now.
Q1.
Okay, what do you want to use Q1 on?
As tangent, we can do sine. I can do 2 sine of the whatever alpha thing is minus sine over cosine times that cosine.
Mhm.
And then that's just going to cancel out. We can do 2 sine.
Go to whole slow down. But yes, That's good.
Okay, so I'm gonna put 2 portions of it cancel out.
Everybody good with what she saw, what she did there? Okay. Before we go on and say what happens next, Lexi, what did you see in that previous step that made you want to use Q1? Good. Yeah, so that's the right idea. She saw that in the rest of the problem, all I have are sines and cosines, and I have a way to convert tangent to be in terms of sines and cosines. So I should be able to do some combining things together after I do that, right? If I can get everything down into the same kind of trig function, so there, instead of having 3 separate trig functions in the problem, now I would have just 2 separate trig functions, sine and cosine. So that makes things a little bit simpler. So that's a good idea. In general, if you can do that, those are good things to do. Matt? Yeah, so that's where she was going next, is that we absolutely can cancel those out.
And then 2 sine minus 1 sine is going to be sine
Mm-hmm. Alpha.
yeah.
Yep. And that's done. And I would say that that's the best way of doing that one. There's no faster route for that one. Is everybody okay on that one?
Yeah, it's kind of hard.
Yeah, it's not the easiest process in the world, but you know what? Like, you know how you get better at it? Practice. Is the more familiar you get with the identities, and the more you know what you can do with them because you've used them, the faster these go and the easier things get. But you have to sit there and like kind of struggle through them for a little bit until you get some intuition, kind of figure out like what is generally good ideas to do and what are generally not good ideas to do. And it's hard to do that until you've really spent some time with it. So, I mean, I could tell you general patterns of things that are often good ideas to do. The problem is more often than not, we run into a situation where it's not a good idea to do that. So just, it's helpful to just let you kind of explore on your own a little bit about what are good ideas and not good ideas. All right. I would do an algebra thing first. And the reason I would do an algebra thing first is because 1 minus sign and 1 plus sign are not things on my identity list. Anywhere, right? There's no identity I can really use. I could turn sine into 1 over cosecant, but now I have a fraction inside of a fraction, and that, like, it might get me somewhere, but it doesn't seem like it's going to be anywhere good. Yeah, so if I wanted to add these together, what do I need to have? A common denominator. What would that common denominator be? Common denominator? Well, let's just take an aside here for a moment. What if this was this problem, where we did this last year in Algebra 3-4? If I want to add these two fractions, what would the common denominator be? Guys, I'm so sad. I did such a bad job.
The minus subtraction.
None of those things you're saying are like a common denominator. What do you mean by FOIL? You don't know. Hannah, what did you say there? Okay, so what are we going to multiply to the first fraction here?
1 plus x.
And what would you multiply to the second fraction?
1 minus x.
Yeah. That's the idea. So the common denominator is literally just 1 plus x times 1 minus x, right?
Oh, yeah.
You guys remember doing that?
Yeah.
Okay. So up here above, in the problem we actually care about, what would our common denominator be?
1 minus
Times?
1 plus sign.
Yes, there you go. So to the first one, we'll multiply a 1 plus sign. And to the second one, we'll multiply a 1 minus sign. So what am I going to have to do when I multiply the denominators together? Okay. Sure, we can just write it as one line. That's fine. No, I don't want to do that, but I was going to multiply things out first, but we don't have to do that. No. So in the top, I have two things that are being added together, and in the denominator, I have two things that are being multiplied together. So they're not the same thing. So we cannot cancel things. But what can we do?
We can.
You can't do 1 minus sign on top and the 1 minus sign.
Oh, yeah. Right, so you're adding.
No.
Okay.
That's mathematics.
No.
Yeah,
No.
can't you do 1 plus sign and then 1 minus sign? Don't those like equal 0?
So you want to combine the like terms on top.
Yeah.
Is that what you're saying?
Yeah.
That's okay.
Okay.
They don't give you 0, though.
They give you 1.
They don't give you 1
They give you y.
or y.
They give you what?
Brian?
They give you sign.
2.
What?
1 plus 1 is 2. Sine y plus negative sine y is 0.
Wait, that's a negative.
This one and this one added to give you 0, and you're left with 1 plus 1,
Oh, yeah.
right?
That makes sense.
Okay. Okay.
And then
Do we see any trig identity to use yet? We haven't used the trig identity yet. No. What should we do then?
keep doing 1 term.
Let's multiply the denominator out.
Yeah.
Because maybe at that point a trig identity will present itself to us. So I'll just FOIL that denominator. Oops. Okay, so there we FOILed everything out. What do you notice? Yeah, those guys cancel out, right? Mhm. Good. So Hallie says that she knows that 1 minus sine squared is cosine squared. That's one of our altered versions of P1. I'll call that as P1 star. So remember when I wrote those alternate versions for the Pythagoreans and asked you to write them in next to it?
Oh, yeah.
That's what we looked at there. Mhm. Everybody good with that? Okay.
Okay. Then we take
There's one more thing to do.
like adding this or like
There's one more thing to do.
oh.
What was that, Brian? R5. Good. What is R5 going to give us then? 2 still. Secant squared. Wow. Look at what R5 says. secant is equal to 1 over cosine, right? So secant squared is 1 over cosine squared, right? That's what we have. We have 2 times 1 over cosine squared. So that's it. Then we're done, because we're down to a single trig function without a fraction. I mean, I acknowledge in the previous step we're at a single trig function, but I think we all will agree that no fraction is simpler than fraction, right? So if you can make it so there's no fraction, that's a little bit better, in my opinion. Okay. What do you guys think? It's hard. That's fair.